So as we discussed earlier, that depending on the amount of diamagnetic current, the shielding will be different, and the value where the signal will appear will be different. These values are known as chemical shift values. So chemical shift value are the values of NMR signals where they will appear on the ppm scale. Ppm scale is also known as delta scale. Okay, so let's look at uh, effect of electronegativity of nearby atoms and hybridization and diamagnetic effect from pi bonding. So first, let's talk about electronegativity. How electronegativity uh, affects the chemical shift value. So this table shows the chemical shift value of protons connected to a carbon atom, which is further connected to some electronegative element. For example, first one is fluoromethane. So in this, all of these three protons are equivalent, and then it's connected to fluorine, highest electronegative element. And the chemical shift value of these protons, these three, is 4.26. Okay, so note down this value. Now, if instead of fluorine we attach oxygen, then the value of hydrogens becomes chemical shift value of these protons is at 3.47. Instead of oxygen, if we connect chlorine, then in that case, it is 3.05 and so on. You understand where I'm going. Can you notice the trend? So what is the trend here? So what can we say the effect of nearby electronegative element on the chemical shift of protons?
The greater the electronegativity, the greater the chemical shift.
We call it more downfielded or deshielded. Yes, yeah, but you are right. Yeah, higher number. Okay. So that is correct. So greater the electronegativity of any of the neighboring element, the chemical shift will move towards the downfield region. So higher number of delta value will be observed. Keep one thing in mind, this effect of electronegativity is quite short ranged. For example, in this particular example, the electronegative element is directly connected to carbon where hydrogens are also connected, right? So they're quite in the same vicinity. But if we add one more carbon in the middle and then connect an electronegativity element such as fluorine, see now it's two carbon away, right? So two carbon away. Then the effect is only about 10%, right? So it's not that great. And after three carbon, electronegativity of nearby element has zero effect. It does not affect after three carbon. If it's more than three carbon away, it doesn't affect at all. So it has to be, uh, in order to give this trend, this effect has to be directly connected to the carbon where protons are connected. Okay. So the lowest electronegativity element we have is silicon, which is 1.8. That's why it's arbitrarily given zero. So we call that a zero standard because that's where the maximum shielding takes place. So that's the effect of electronegativity. Any question about effect of electronegativity? Okay. Next, let's look at hybridization of adjacent element. Oh, sorry, adjacent atoms. Okay. So this one is sp3 hybridized. This one is sp2. This is sp. Okay. Now we know that sp3 has 25% S character. How much S character is present in sp2?
33.
33% S character. And sp is 50%, right?
Yep.
And in previous chapter, we also learned that more S character means more electronegativity. Why? Because s orbital is spherical, p is elongated, so s holds the electron more closer towards it, so more electronegativity. So in other words, this one will pull the electron towards itself maximum, right? And this one will not, right? So it means this one here, maximum shielding, right? So the signal will be closer to 0 or lower chemical shift value, which is true. In sp3, protons bonded to sp3 carbon, the signal do appear at quite low value, 0.8 to 1.7. Okay. Now, the signal from a proton bonded to sp hybridized carbon, it is high relatively, between 2 to 3, so that's okay. But the problem is this one. Okay, so let's. So for sp, the signal appears at 0.8 to 1.7. For sp, signal is between 2 to 3, right? If we go with the trend, what do we expect sp2, which is right in the middle of S character? Wouldn't we expect this value to be in the middle of sp3 and sp? Yeah?
Yeah.
But that's not the case. It is absurdly high. It is 4.6 to 5.7. So it means something else is going on apart from S character. S character is one of the reason, but there is something else is also going on. Okay. So these are the three cases I was discussing. Okay. So for sp3 here, so they are not in the order. Now, why it's so? So it can be explained by a phenomenon called ring currents or pi electron ring currents. Imagine this is the triple bond and there is a hydrogen here. Okay, let me show the sigma bonds with red color. So these are the sigma bonds and that's our hydrogen. The blue ones are pi bonds. So pi bonds are around it. So these are the pi electrons. And these pi electrons, they are rotating this way. They are rotating this way. When they rotate this way, they create their magnetic moment in a ring form. And that magnetic moment is going this way. Okay. So from outside into the middle of the bond. So this one shows a better picture. So the pink circle around, you see these are the pi electrons, the two pi bonds or pi orbitals. And the ring, so pi orbitals have pi electrons, they rotate in this direction, they create a ring current. This green big arrow, that's the external field. So the ring currents, and there is the hydrogen right in middle. If you see the ring current, where the hydrogen is, are they opposing the external field, or are they aligned with the external field? So if you see the direction, so the ring currents are opposing it, opposite. Okay, so if they are opposite of external field, hence they are shielding it. Okay, so even though this proton, this one, is connected to sp hybridized, and sp is more electronegative, and it's supposed to pull the delta value down, but because of the ring current, it gets more shielding. That's why the triple bond, proton connected to a triple bond, does not go that much downfield what it was expected to go to. So that's why the S, it is relatively high, between 2 to 3. So proton connected to triple bond, that's because of the ring currents of pi electrons, because they are shielding it. Okay, so any question? Now, if in triple bond the ring currents are shielding it, then why in a double bond we don't see that kind of a shielding? Why the signal is towards the downfield region? Why it's towards the deshielded region? 4.6 to 5.7, that's quite high. That's quite deshielded region. The answer is can again be attributed to the ring currents of pi electron, but now we have to look at where the hydrogens are. In case of a triple bond, hydrogen is present on top of the ring current where the direction of magnetic field, so it's a circulating magnetic field. So like that, it's a circle. So in this way, in the outside of circle, the direction is towards the applied field, the outside is towards, but inside is opposite, it's downward. It's a circular magnetic field. And it happens that in case of a triple bond, the hydrogens are present in the middle of the circle where the ring current have opposing direction than the external magnetic field. So that's why they are protecting it, or they are shielding it. But in case of a double bond, again, there are same ring currents, but the protons are outside of the circle. So in outside of the circle, the ring currents are in the same direction as of the external field. So hence, instead of shielding, they are doing the opposite. Now they are de-shielding it. De-shielding it means they are sending uh, this signal even more towards the downfield region. That's why we see the signals or the chemical shift value of hydrogen nuclei bonded to a carbon with a pi bond at high chemical shift value. Okay. Any question about the ring currents? Okay. So if I have a carbon-carbon double bond and hydrogens are connected here, so ring currents go from this direction to this direction. So where the hydrogens are, the ring current are aligned with the external field. Hence, they do not shield it. Therefore, the signal of hydrogen or protons connected to carbon-carbon double bond is towards the de-shielded region or downfield, not upfield. If hydrogen happened to be in this region, then it would be protected. But unfortunately, hydrogens in double bond are not there, not in this point. So that's the entire reason. In case of benzene also, benzene structure is exactly planar structure. So all protons are outside the circle. So in this case also the ring current originate from the middle and they go here. So all hydrogens are in the same direction of ring currents. So there is no shielding given to these protons by the magnetic ring currents, by electron currents. Hence, the signal from aromatic protons or protons which are connected to aromatic carbon, what do you think? Where would they appear? Low field or high field? Or downfield or upfield? Or high chemical shift value or low chemical shift value? Any guesses? Yes, so it will be at high value. And if we go back to our table, we can see that aromatic protons are at between 6.5 to 8.5, even higher than alkenes. Okay. There's another important information which we can obtain from NMR spectrum, that's called signal splitting. When we actually conduct the NMR spectrum, it does not look like a single peak, but instead it looks like a split signal. For example, this signal, that's a zoomed version of this signal. This looks like a split into 4 different segments. So this one is known as quartet, and this signal is split into two different signals, that's known as doublet. So this is known as splitting of signal or signal splitting. So in NMR signals, they may be singlet. Singlet means single peak, no splitting. Doublet means 2 peaks or double or one splitting. Triplet, quartet, or multiplet, and so on. Why do they split? This splitting of NMR signal is as a result of influence by neighboring nuclei. And they follow N+1 rule. So in simple words, what's the meaning of N+1 rule? Let's say if I have this molecule, how many sets of equivalent hydrogens are present in this molecule?
2.
2. So how many signals do I expect?
2.
2 signals. So that is correct. So one from this one, the other one from this one. Now we know the table. So can you give me some idea? So if this is 0, that's a 0. Where would signal A be and where would signal B be? Range. Yes, what do you think? Where signal protons from A group will show up? Any guesses? It's between 0 and 10. Any number is. So what kind of protons are these? Connected to carbon, is carbon sp3, sp2, sp?
SP3.
sp3. And alkyl group connected to sp3, where do they appear normally?
0.8 to 1.
Around 1, right? But because there is a chlorine nearby, it's not directly connected, nearby will have some effect. It will be a little bit more than one, right? So we expect one signal to be here. The other one is direct, these protons are directly connected to chlorine. So if they are directly connected to chlorine, oops, sorry, where was it? Electronegativity there. So it will be close to 3, right? Around 3. So this will belong to signal A, and around 3 will have signal B. Which signal will be larger, A or B? Or same size?
Will B be larger?
A will be larger because A is coming from 3 protons, B is coming from 2 protons. More number of protons in a signal, bigger will be the signal, right?
Right.
Yeah. Now, although I have plotted this as a single peaks, but actually it's not gonna be single peak. Signal A, which is here, how many protons are present on the neighboring carbon to signal A?
2.
2. So it is n plus 1 rule. It means the signal A will split into 2 plus 1 peaks. So 2 plus 1 is how many? 3 peaks. So therefore, signal A will not look like a single peak, but instead, that's how it will appear. It will appear like a 1, 2, and 3. All 3 will not be same sized. The middle one will be larger. The other 2 will be same size, half the size. So this signal is known as triplet. Okay. Signal B. So in signal B, how many protons are present in the neighboring carbon to signal B?
3.
3. So it will split into how many peaks?
4.
3 plus 1 or 4 peaks. So therefore, signal B, instead of looking like a single peak, it will look like this one, 4 peaks. Again, the intensity of the side 2 will be less and middle 2 peak will be high. We'll learn about how to figure out the intensity in a couple of slides later, but that's the meaning of signal splitting. Okay. So we look at, so this is extremely important information. So if we don't know the structure, if I look at the signal from A, I can immediately tell that in the neighborhood of A, there are 2 protons because the signal is split into 3 peaks. And if I look at the B, I can immediately tell that in the neighborhood of B, there are 3 protons present because signal is split into 4 peaks. That's where we can back calculate how many protons are present in the neighborhood of those equivalent hydrogens. Okay. Okay. So if we have this compound, so that's A, let's call this A, let's call this B. So A has how many hydrogens in the neighborhood of A? How many hydrogens are present?
1.
1.
1. So therefore, signal from A will split into 1 plus 1 equals 2 peaks. So that's why we get a doublet here. And signal from B, that's 1 proton at B, but in the neighborhood, we have 3 protons, right? So B will split into 3 plus 1 in a quartet. Okay, so that's what it looks like, quartet, and this is a doublet. So any question about signal splitting? how to calculate in so this is known as multiplicity of signals. Okay, so let's try another example. So let's imagine if I have okay, this compound, this one, how many groups, how many equivalent hydrogen groups are present? Or in other words, how many signals will be obtained from the NMR spectrum of this compound?
3.
3. So one from each CH3 groups, right? So it's one from this group, the other one from here, and then the third one from here. So signal from group number A, which you can see on the screen, what will be the multiplicity of that signal? Or in other words, how many peaks this signal will split into?
Just one peak?
Say that again.
Just one peak?
That is correct. Just one peak, because in the neighborhood, there are no hydrogens, right? That is correct. How about B? So signal from B will split into how many signals?
4.
4 is correct, because in the neighborhood, there are 3 hydrogens and it will split into 3 plus 1, 4. How about signal from C?
2.
2. So C will give us a doublet, B will give us a quartet, and then A will give us a singlet. Okay. Ooh, that's the exact problem we just saw. Well, it's similar. Okay, so let's predict one more time. So you tell me whether the signal will be a singlet, doublet, triplet, quartet, or so on, right? So how about this signal?
Singlet.
I'm gonna use, okay, this one. These 2 hydrogens will give us how many? What kind of signal?
A quartet.
Quartet is correct. I'm just gonna use Q. And how about this one?
A triplet.
Triplet is correct. In B, first tell me how many signals I expect to obtain.
Just 2, because there's symmetry.
Yep, 2 signals, because there is a symmetry. So these 2 are equivalent, and then these 2 are equivalent. So these 2 will give. So let's call this group A, and let's call this group B. So group A, what will be the multiplicity of group A?
3. 3 signals.
Or triplet, right?
Yeah.
How about B?
A quartet.
A quartet is correct. Now, if you are confused that, oh, there are 3 here and there, no, we don't. If they are equivalent, then we just look at each one of them and see how many are in the neighborhood. For example, we just look at this one because the other side is equivalent. So whatever happens to this side, same thing happens to the other side. So in this side, there are 3 hydrogens in the neighborhood, so it will be quartet. The other one will do the same. Okay. Here we have one signal will arrive from these 3 hydrogens, then this one, and these ones will give us another common signals, so 3 signals. So it's a good idea to expand the structure first. That will give us a better picture. So it's CH3, CO, CH, right? So what will be the multiplicity of this signal? Let's call this A. Singlet, right?
Yep.
These two are equivalent. Let's call them B. What will be the multiplicity of B?
Doublet.
Doublet is correct. Finally, this one. What will be the multiplicity of this one?
Quartet.
Well, no, because all of these three and these three, 6 of them are in neighborhood. So and they are all 6 are equivalent. So it will be 6 plus 1. So it's 7. So 7 is called septet, or you can just say it's a multiplied. It's a 7. Multiplicity will be 7 in this case.
So we do count the total number
Yeah, if they are directly connected to
when
it,
they're
yes.
even if they're equivalent groups.
Yes, we
Okay.
do. In example B, we did not count because the other ones are not directly connected to the hydrogen or that one.
Right. Okay.
Okay. Now, where does this multiplicity arise? What's the origin of this multiplicity? So this is because of a phenomenon called spin-spin coupling. Okay. So it means that the nuclear spin of one proton couples with nuclear spin of neighboring proton. Okay, if the neighboring proton is 3 bonds apart, for example, right? Let's call this A and let's call this B. So hydrogen A and hydrogen B are how many bonds apart from each other? So 1, 2, and 3, right? So 3 bonds apart. Then they can couple with each other. Okay, so it means the magnetic moment of A will be affected slightly by a magnetic moment of B, and so on. When they are 3 bonds apart, this kind of coupling, these kind of hydrogens are known as vicinal hydrogens. And this coupling is known as vicinal coupling. Okay. So the splitting of this peak, is because of vicinal coupling. How this happens, I'll explain in next slide. But any question about what are vicinal hydrogens? And so, for example, okay. How about red and red hydrogen atoms? Are they vicinal? Red and red. Anyone?
No.
That is correct. They are not. Because red and red, they are only 2 bonds apart. They are not. How about blue and purple hydrogen, are they vicinal?
Yeah.
And that is also correct. They are visible. How about red and purple? Are they vicinal?
No.
That is correct because red and purple are 4 bonds apart. So 1, 2, 3, and 4. Now, if red and red are not vicinal, what they are? What are they? Red and red. You said they are not vicinal, right? So then what are they? You know it. Yeah, well, we talked about it. Remember, they are connected to same sp3 carbon.
Just equivalent.
They are just equivalent. Yes, that is correct. So they are just equivalent. Now the last question, the tricky one. How about green and purple? Are they vicinal, equivalent? What are they? Or neither? Yeah.
Wouldn't it also be vicinal, green and purple? Because 3 bonds apart.
And you are correct. Yep. They are also vicinal. Remember, they can rotate. Even though I showed green up, but they are free to rotate. They can come down also. It's sp3. If you create a model, bonding model, you'll see they all can rotate around it. Yes, red and green are also vicinal. Okay, so any vicinal hydrogens, they can couple with each other. Equivalent hydrogen gives same signal, but vicinal hydrogens give different signals, but they can couple with each other. So they affect the signal. So they cause the splitting. So let's see how the splitting takes place. Okay, so these are vicinal hydrogens, so they can couple the same concept. So let's talk about here. I think I'll use here. So let's take an example of these two protons. They are vicinal, as you can see, and there can be other neighboring things else. We don't care what else is connected. Now imagine that the NMR signal from blue is here, right? So this is the signal, supposed signal of blue at some value here. So this is the shielding region as we go this way, and this is the de-shielding region. So 0 is this way and 10 is this way. Okay, so just remember that. Now, as hydrogen is blue hydrogen is spinning and it's giving a signal here, the green hydrogen can do two things. Green hydrogen is also spinning, right? So if the external field is this way, green hydrogen can spin in such a way that it also aligns with the external field, right? Green hydrogen can also align. If it aligns with the external field, the neighboring blue hydrogen will experience stronger field, right? Yeah?
Yeah.
So if it's experiencing stronger field, the signal where it was supposed to, that signal will now move, right? The other, okay. So So instead of protecting it, right? So if it aligns with the external field, instead of protecting it, instead of shielding it, it's now doing it more de-shielding, right? So the blue signal will now shift. Instead of appearing in this region, it will appear, sorry, it will appear here. That's what will happen. The other thing it can do is that neighboring hydrogen, the green one, can spin in such a way that it aligns against, creates a magnetic field which is opposite of external field. If the field generated by the neighboring or the vicinal hydrogen, green in this case, is opposite, the blue one gets shielded a little bit, tiny bit, right? So if it gets shielded, the signal from the blue will shift this side. Okay. So now if you ask which one it will be, the answer is it's a 50-50 probability. Half of the time, the green one will align opposite of external field. Half of the time, it will align along the external field. So half of the time, the signal from blue will be de-shielded. Half of the time, the signal from the blue will be shielded. So that's why instead of getting one signal in the middle, we don't get that. We get this signal. Okay. So split signal. So this is a, well, the way I shown here is they look quite apart from each other. They are not that apart. They actually are just tiny bit apart. So this is called coupling. So, and the distance between these two is tiny, quite tiny. So this is known as coupling constant, or J. So this is a coupling constant. Okay. Okay. So that's what this is showing on the plot here, that for proton A, if the nuclei, the neighboring B couples, so external field is this way. If it rotates in such a way that is external, it is opposite of external field, then the signal will shift to upfield somewhere here. If it's aligned along with that, then it's downfield. So in the spectrum, we'll get this a doublet here. The distance between two peaks is called JAB. AB, where AB refers to what protons are we talking about, and this is known as a coupling constant. Okay. When we have multiple, okay, let's take a look at this. Graph the multiplicity. So in this case, there is a symmetry here. So therefore, these two are equivalent hydrogens, and then the other two are also equivalent. So this one and this one are also equivalent. So we have two sets of hydrogen. For the red set, neighboring one, then in the nearby, we have only two hydrogens. So the signal from red will split into a triplet. And that's what we see, a triplet here, which is this signal. The distance between, so this tiny distance here, this tiny distance, this one, that distance is the coupling constant, J. Okay. Now the coupling constant J depends on the angle between the vicinal hydrogens. Uh, Coupling constant is maximum when this angle is either 0 degree or 180 degree. So then the coupling constant is maximum, or in other words, in that case, the splitting is highest. And it's minimum when the angle is alpha. Just remember, I'm sorry, angle is 90 degree. So let's take a look at it. So in these two cases, so they are exactly opposite of each other. So here the angle is 180 degrees. So now that's quite high splitting. So 15 up to 15 is quite high. And here the angle is almost zero, sorry, almost 90 degree. So this and this, if you look at it, it's almost 90 degree or close to 90. Therefore, coupling is quite small. Okay. Here again, the angles is almost 180 degree, if you think about it. So that's why again, the coupling is quite high. So depending on what is the angle between the vicinal hydrogens, the coupling constant will be uh, anywhere from 0 to 18 hertz. It's not that big number, but it is enough to give us some significant information about our system, about our molecule. Let's talk about the relative intensity. So we already discussed the case in which there is only one neighboring proton. Let's talk about a case in which there are two neighboring protons. So we have this hydrogen and we have two neighboring. So if I look at this signal, the signal from here, and that's the external magnetic field, right? One possibility is that both of them are opposite, both the neighboring hydrogen. So both of these are vicinal, right? So one possibility is that both of them align against the external field. If both of them align against the external field, the signal from this one will be shielded quite a bit, right? So it will appear here. The other possibility is that both of them align with the external field. If both of them align with the external field, this signal will be quite a bit de-shielded because they are with it. So it will appear somewhere here, right, in this region. The third possibility is that one of them is with the field, the other one is against the field. Okay, so then the signal will be right in the middle, right? The fourth possibility is that now the bottom one is against the field and the top one is with the field. In this case also, the signal will appear in the middle. So when all of these four cases are averaged out, our signal, the actual signal, will look like this. And what is this actual signal? Triplet. And where the intensity is 1:2:1, which means that the middle peak will be twice as much as higher than the side two intensities. Because for the middle one, there are two possibilities which give us the middle signal. Any question? Now let's look at a system where there are three neighboring protons. When there are three neighboring protons, one possibility is that all three are against the field. So when all three are against the field, that's the only single possibility. Then the signal will be here, upfield. So this is the upfield. Another possibility is when all three are upfield. Okay, so when all three are along the fields, right? So when all three are along the field, then the signal will be in this way. Now, there are three possibilities in which two of them are upwards and one is downward. So more along the field, less against the field. So then we'll get this signal. And then fourth and final possibility is that two of these three are against the field and one of these oriented with the field. So again, there are three chances, then we get that. In that case, our signal will look like a quartet, like that. And the intensity will be 1:3:3:1. Means the middle two peaks will be same size and they will be 3 times as larger than the side two peaks. Okay, so that's how we can figure out the intensities of the peaks when they split. Now we don't have to draw all these possibilities to figure out the splitting pattern. There is a simple way. This is called Pascal's triangle. And this triangle will help you to figure out the relative intensities of peak when they split. All you need to do is you start with one. When we have a singlet, then there's just one peak. When we have so in singlet, we have only one peak. So peak will appear like that. When we have doublet, so this is one peak. So you draw 1 and 1, right? So it will be 1 and 1 means equal intensity. So doublet look like that. When there is triplet, okay. So what we do is we draw 3 lines. That's triplet. But now we need to figure out the intensity. So the way to calculate the intensity is we look at the lines. So this line is in the middle of these two lines. So we add these two numbers. That's 1 and 1. So when we add them up, this number comes out to be 2. Okay. This line is on the side and there is no number here. So 1 and no number will stay 1. This line is on the side. So 1 and no number here. So that's also 1. So therefore that when we have triplet, the intensity will be 1:2:1, or the triplet will look like 1, 2, 1. So the middle one will be twice as large as the side one, side 2. Is that okay? Is that clear?
Yep.
When we have quartet, so quartet, draw 4 lines, 1, 2, 3, and 4. Now we need to figure out the intensity. So the side lines, so it comes from here, 1 and no number. So 1 plus no number will still be 1. The intensity of the middle line comes from these two numbers. So 1 and 2. 1 plus 2 is how much? 3. So this line is in the middle of these two. So 2 plus 1 is how much? 3. And 1 plus no number is 1. So intensity of quartet will be 1:3:3:1, or it means it will be 1, 3 times, and 1. So quartet looks something like that. I'll go one more time and next you can try by yourself. So quintet means 5 peaks. So 1, 2, 3, 4, and 5. So intensity of the first one will be 1. The other two will be 1 plus 3. 1 plus 3 is 4. So 3 plus 3, 6. 3 plus 1, 4, and 1 plus 1 is 0. So it means when the peak splits into 5 multiplicity or quintet, the intensity will be 1:4:6:4:1. Okay, so mine may not be as accurate, but that's what it's gonna look like. And so on. You can continue to as many multiplicity level as you want. So any question about signal splitting? Okay, so let's, so this we discussed. There are some complex splitting pattern which I'm not gonna discuss here because we will rarely see it. So I'm gonna skip over complex, but I will make it available on those. Okay. Okay, so we're gonna skip over the complex splitting pattern. So let's take an example of uh, the normal, because complex splitting pattern we don't observe in most of the cases. So we'll stick with the simple ones. This spectrum is NMR spectrum of 1-chloropropane. As we can see, we have 3 equivalent hydrogen groups, A, B, and C. Group A is connected to a carbon which is bonded directly to chlorine. And we know that whenever a protons are connected to carbon directly bonded to chlorine, the signal appears approximately 3 delta scale, 3 point something. And if we look at the spectrum, we see a signal at 3.5-ish. So this signal belongs to these 2 protons, right? So in signal A, how many vicinal hydrogens are present to group A? So all hydrogens on B are vicinal to group A, right? So how many vicinal hydrogens are present?
2.
2 of them, right? If 2 vicinal hydrogens are present or 2 neighboring hydrogens are present, what will be the multiplicity of group A? So that will be 2 plus 1 equals 3, right? And so it will split into a triplet. And if we look at the zoomed version of A, we'll see it does indeed split into 3, and the intensities are 1:2:1, or it means the middle one is twice as large as the side 2 peaks. Does that make sense?
Yeah.
Yeah.
How about C? So C has how many vicinal protons? Or vicinals are the 3 bonds away or nearby, the neighboring one. Yes.
5.
2.
Oh, wait, sorry. I was thinking B.
A is not vicinal to C, right? Oh, you were thinking about B?
Yeah, sorry.
Yeah, for C. We'll look at B at the end. Okay, so C will also split into a triplet. And C is farthest away from chlorine. So at that position, chlorine electronegativity has no effect. And we know that sp3 bonded protons appear anywhere from 0.8 to 1.7. So only signal which is triplet, and 0.8 to 1.7 is this one, and it is indeed triplet. Now B is, of course, you already said there are 5 protons in the neighborhood. So it's gonna split into, multiplicity will be 6, and 6 is known as, oops, where was the Pascal? It's known as sextet, right? So 7 is septet. So there are 6 multiplicities. So I was just gonna look at the ratio. So it's 1:, I don't remember. Okay. 1:5 is to 10 is to 10 is to 5 is to 1. So that is the ratio. So this is a 1:5:10:10:5:1. Okay. So any question about splitting patterns? So in the beginning of this chapter, when we defined equivalent hydrogens, we kind of oversimplified it. Okay. When we said if there is a plane of symmetry and they are equivalent, that was the oversimplified explanation of equivalent hydrogens. Now, depending on the symmetry of the molecule, those hydrogen which may look equivalent symmetrically, they may fall into three separate categories. And those three separate categories are, they may be either homotopic, they may be enantiotopic, or they may be diastereotopic. In the beginning of this chapter, whenever there was symmetry, we just said that they're all equivalent. But no, they may not be equivalent. They may be in these three categories. The simplest way to tell what, so this is known as topicity. The most simplest way to visualize the topicity is that we substitute the nuclei with its another with an isotope of itself. For example, let me give you an example. Let's say we have this molecule. Okay, so how about these two hydrogens shown here? Are they equivalent? Well, wait. Okay, how about now? Is there a symmetry? Are they equivalent according to symmetry? Yeah, anyone? So the answer is, you would say yeah. But the situation is a little bit more complex. The way to understand the topicity is that if these two hydrogens are equivalent or not, replace one of the hydrogen with the isotope. So let's replace this hydrogen marked here with its isotope deuterium. When we replaced it, then you need to answer, after replacing, did we create a new chiral center after replacing with it? Did we create a new chiral center? What do you think?
No.
The answer is yes, no. Okay. If we did not create any new chiral center, then whether you do this one or you do this one. Okay, so no new chiral center is created, replacement of either one. So then these two are known as homotopic. So homotopic protons are those protons in which no new chiral center is created or generated when we replace them with their isotopes. Does that make sense? Okay. So achiral stays achiral. So this is homotopic hydrogens. Homotopic hydrogens are equivalent under all conditions. So they are equivalent. All homotopic hydrogens are equivalent. Just remember that. Let's take an example of another molecule. So this is chlorofluoromethane, and there is no chiral center, so it's achiral. But if we substitute either one of these two hydrogen, either one, doesn't matter which one, will that create a chiral center?
Yep.
Answer is yes. So when we have two protons which otherwise looks equivalent because they are connected to the same carbon, we would say, oh, they are equivalent, right? That's what we said in the beginning, yeah? That was the oversimplified version, right? So the correct version now is that if an achiral molecule produces a chiral center after replacing with an isotope of a proton, then these two are called enantiotopic protons. Now they are enantiotopic. Enantiotopic atoms, they have identical NMR shift or NMR chemical shift in achiral environment. However, if you put them in chiral environment, their NMR shift will be different. So these two protons under what are under achiral environment? Achiral environment is maybe you dissolve them in an achiral solvent and then take the NMR. Then their signal will be same. But if you dissolve this in a chiral solvent and then take the NMR, the signal of these two hydrogens will be different. So they have different chemical shift in chiral environment. Okay. The last category is that if your starting molecule is chiral and then you replace one of the hydrogen atom with another isotope and we create another chiral center. So now we have two chiral centers. So in the beginning we have only one chiral center, but after replacing now we have two chiral center. Okay. So if we replace one with the other one, so we will create another chiral center. So these kind of compounds, they are not mirror images of each other. They are diastereomers. Hence, these compounds are, these groups are known as diastereotopic groups, or these protons, nuclei, or these proton atom, or these hydrogen atoms are diastereotopic. Diastereotopic hydrogens have different chemical shift under all conditions, regardless of whether they are in chiral environment or achiral. They will show different chemical shift under all. So therefore, these two hydrogens, although they are connected to same carbon, and we would have said, oh, they are same. They're equivalent, therefore they should give the same signal. However, they are diastereotopic and their signal will be different. Okay. So any question about what is homotopic, what is enantiotopic, and what is diastereotopic? Okay, so let's try an example. Let me see if I have for empty space. Okay, please let me know the green protons, are they equivalent, homotopic, enantiotopic, or diastereotopic? In the beginning, we would have said they are equivalent, but they're not. So they are either homotopic, enantiotopic, or diastereotopic. So let me know what they are. What do you think? So the way to determine is replace one of them with its isotope, deuterium, and then see if that creates a new chiral center. Okay, so will that generate a new chiral center if we replace one of the green hydrogens with deuterium?
Yes, it would.
It would, right? So if it creates a new chiral center, then they are
Antiotopic.
an enantiotopic. Yes, so these two are enantiotopic. Is correct. You're gonna see these kind of problems in upcoming exam. So these are enantiotopic. Yes. Let's try another example. Okay. Yeah. Yeah. The red ones, the red protons, are they homotopic, enantiotopic, diastereotopic?
They would be an topic, wouldn't they?
And that is correct, because if you replace one of them with D, you will create a new chiral center. Now this is chiral, right? So all four are different. So they are enantiotopic. That's correct.
Just to be clear, Professor, if
Yes.
the double bond was not there, this
Yeah,
would be
I
homotopic,
was
right?
coming to that. I was coming to that. Yes.
Oh,
Now,
okay.
yes, that was gonna be my next question. Yes. So what are they now? Are they still enantiotopic?
No, they would be homotopic.
Yes. So now they are homotopic because if we replace them with proton, it's still not chiral, right? So not chiral. So not chiral means they are homotopic. Is that okay? Is that clear? How to figure out the topicity? Let's try
Yeah,
one
makes
last
sense.
problem, and then we'll do some NMR analysis. The green ones, the green protons, are they homotopic, enantiotopic, or diastereotopic?
Is that an antiotopic again?
In this case, it will be diastereotopic. The reason is there's already one stereo center existing here. There's already one chiral center here, right? Already one chiral center, and if we replace the hydrogen with deuterium, oops, sorry. If we replace them, it will generate one more chiral center, right? So now when one chiral center is already there and they create one more chiral center, that would be diastereotopic. And remember, diastereotopic protons give different signal under all conditions. Okay. Okay, so that's all about topicity. So this is an example of diastereotopic uh, proton molecules. For example, look at the A ones, right? So we would have earlier, we would have said that A are equivalent. So protons at position A and A bar, A prime, they are both equivalent. However, if we replace any proton at A or A prime, it will create a chiral center at C. And there's already one chiral center existing at this position. So therefore, A and A prime are diastereotopic protons, and hence they give two different signals from C. So therefore, the signal from A is a, so this one gives a different doublet because at C there is one proton. So signal is a is a doublet, A prime is also a doublet, and they appear close to each other. That's why it looks like a four quartet signal, but it's not a real quartet because we know the real quartet has to look something like that, right? That has to be a real quartet. In quartet, all four signals are not same intensity. But in this case, signal A is four equivalent lines. So it's a doublet, two different doublets close together. And because of the stereotopicity of protons at A position. So all the topics needed for proton NMR were discussed so far. So do you guys have any question? So the main things to remember in the proton NMR is first of all, the uh, chemical shift values, where the chemical shift is expected, right? Is it upfield, is it downfield? So that you can determine uh, by looking at the data chart. And second is the size or area under the curve. That area under the curve will give you that how many equivalent hydrogens are contributing to that signal. And finally, you need to look at the splitting pattern. Splitting pattern will give you that how many neighboring protons are present to that signal. And by combining all that, you can create enough information to figure out uh, the structure, most of the structure. NMR alone cannot provide enough information to calculate the exact structural formula, but it gives quite a bit. The second part of this chapter is C13 NMR spectroscopy. C13 is similar to proton NMR. However, there are few differences. The main difference is that the normal carbon does not give any NMR signal. So it means that the regular C12 is inactive, NMR inactive. We don't get any signal from it. In nature, 1.1% carbon is C13 isotope, right? So let's use a round figure. So we can say that the 1% of carbon is C13 isotope. Okay. So for example, if we have a molecule with 100 carbons chain, like a large molecule with 100 carbon chain, or out of those 100 carbon, only one carbon will be C13. And that one particular atom will give us a signal, right? So therefore, signal from C13 NMR spectroscopy is quite weak. In proton NMR, all hydrogens give us signal, but in C13, signal strength is quite weak. So one way to increase the signal is we have to use a high concentration of sample. Instead of taking the signal from one molecule, maybe you take quite a bit, thousand and millions of those molecules together, and together they will have enough C13. That's one reason. The other thing is because carbon or C13 is so rare, what are the chances that in a molecule we have two C13 atoms together next to each other? What do you think? What are the chances?
Very low.
Very low. And in fact, it's close to zero because concentration of C13 is so low. It's only 1%. So chances are extremely low. So therefore, the presence of neighborhood C13 is almost impossible. So if it's impossible, so C13 signals do not show any splitting pattern by neighboring C because there is no other C13 nearby. The vicinal coupling, so see the proton and in neighboring proton, they split each other signal. So that splitting is not present in C13 NMR because chances of having neighboring C13 is zero, almost zero. There's never a zero chance, but it's almost zero. It's insignificant. So that's a good thing. So there's no splitting, but there's a bad thing is that the neighboring protons, there's always protons nearby. They do split. And there are so many neighboring protons around C13. So this will also split. These are also vicinal and they split so badly that the pattern is extremely complex and it's useless. We cannot get any useful information when protons start splitting the signal from C13. So the way around it is that the C13 NMR is operated in a mode called proton decoupled mode. Now, what is proton decoupled mode? In proton decoupled mode, we bombard the signal with two different frequencies, one for protons, the other one for C13. So when protons are bombarded with another frequency, so they get excited and they come back, they get excited. So that operation happens multiple times during the C13 measurement period. And so during that process, the signal from the proton is zeroed out. If I it's more complex than that. We don't have to know the actual mechanism, instrumental mechanism, but that's a mode. It's called proton decoupled mode. So there are two different radio frequencies are used. One excite all the C13 nuclei. The second one is a broad spectrum, and it causes all protons to undergo rapid transition. So they go in excited state and then the ground state, excited state, and ground state multiple times during single transition of C13. So during that process or during the time scale, the effect of proton is zeroed out. So we get just single signal from C13 nuclei. And this is what C13 spectrum looks like. And it's a proton decoupled. That's why none of the peaks are showing splitting pattern. Again, the zero is the same TAMS signal. And you can see that each carbon, interesting thing is that most of the carbon will not be equivalent to each other. So by just looking at the peak, many times we can tell how many carbons are there. See, in this one, there are 4 carbons and none of them are equivalent to each other. So therefore 4 signals. So interpretation of C13 is quite simple. these are the ranges. The range for C13 NMR goes anywhere from 0 to 220. Important regions are most of the sp3 hybridized, they come from they give signal anywhere from, so sp3 carbon atoms, so their signal will be between 0 to 80. And then sp2 or the double bonds, they give signal, sp2 hybridized carbon gives signal in this region 100 to 160. And carbonyl, most of the carbonyls above 100, it's generally the carbons at carbonyl position. Okay, so this is the data table, and that is C13. So this you can read. I'm just gonna go over some spectrum analysis. Okay. So when we interpret the NMR spectrum, we for alkanes, the signal usually appears between this range 0.8 to 1.7. C13 NMR is alkanes is from 10 to 60, as I explained earlier. In case of alkenes, the proton NMR signal is between 4.6 to 5.7, and C13 is between 10 to 160. So this is the proton NMR spectrum of vinyl acetate. So these are the CH3, sp3 hybridized carbon. The electronegative elements are 2 carbon away, so it's not gonna downfield it too much. It's a little bit downfield in here, so singlet. There's no neighboring carbon, so this signal belongs to D. And okay, so I think I'm gonna stop here. So we will probably have this discussion on Thursday's period. I'm gonna upload this slide with examples on Canvas, and there you can take a look at it. It's already more, we are out of time. Okay, so thank you for staying.